And is that any good? Yeah, okay. Mastered it. Okay, so I'm Dave Leeson. Didn't work. Is it still working? Good. Put it in my pocket. And I wanted to give you an idea of how I got lucky. So maybe you learned something from that. Just a little history. This goes back. This particular talk is one I gave. I was invited to give a talk on the subject of the 50-year history of phase noise, starting from the Dark Ages and up to today where we know everything. My first reaction to it was it can't be 50 years, but it is. My background was when I was 4 years old, I fell in love with ham radio. I still get a shiver thinking about, oh, that's from someplace else, and those are other people, and it's Morse code. Wow. So that was what I always wanted to do. And as soon as I could, I got to be a ham operator, and I got a job in a radio store. A very kind guy put me to work, taught me how to fix radios, which is still useful today, because once you learn about diagnostics, you never forget it. And anytime you design anything, it doesn't work. And so now you have a diagnostic problem. And so learning about diagnostics and the discipline of it was terrific for me. As soon as I was old enough to be insured, I went to work at Hughes Aircraft Company because they were all run by hams. And I started there while I was still in school. Used to go there summers and vacation weeks and that sort of stuff. And that was a company that worked on Doppler radar and then eventually on spacecraft, like communication satellites and moon landers. So it was terrific education for me. And all the while I'm working at Hughes Aircraft learning about Doppler radar, which I'll talk a little bit more about, I am going to Caltech and getting my bachelor's, and then I went for a year at MIT. And it was too cold for a California kid, so I came back to Stanford. And so by 1962, I had my PhD here. And my subjects were nonlinear frequency multipliers. So I was a nonlinear guy. Power series, harmonic balance, linear time invariant, linear time variant, that sort of stuff. So I don't know if I invented it or not, because there was a book that I used that had all that in it. And so I assume that's the secret, by the way, is if you can find a problem and then you can find the answer to it that doesn't look like the answer to it, you're home. And I'll describe some interesting things that have happened along the way. So, okay, so here's, before that, just some preliminary generalities. When I was a kid, I read an article in a science fiction magazine called Will We Fly to the Stars? Everybody likes science fiction when they're a kid, so I did. And the answer was no, that it takes so much energy to send finite rest mass particles that we will use zero rest mass particles to get around. That is, communications will always dominate transport because it's way less energy consumptive. It doesn't require labor. And sure enough, that confirmed my idea that that was the career for me. And so I've always enjoyed being in the business, and that's what I did all my life. One of the things I learned early, and I've taught this in a lab that I taught, that experiment trumps theory. Theory is wonderful, but theory is usually created at a time when there isn't any practical example. I mean, a lot of the mathematics goes back 200-300 years. They weren't thinking about what we do now, but it's still useful because they were thinking about something else. But the proof of the pudding is whether you can actually create a measurement that says, oh, that's pretty useful theory. And the other issue is that, and this is the most important thing I learned as a graduate student. I still remember the lecture where the professor leaned forward, the model is not the thing. Don't forget that. You see people with a computer and it's a model of whatever it is. A circuit model, propagation model, whatever it is. And they talk about it as if it were real, but it isn't. It's an approximation. And it may leave something important out. You have to know that. So the model is not the thing was the most important thing I learned here as a graduate student. It took me 3 years to learn that, but I did other things. But first of all, as you know, everybody's wise to the idea that a linear model won't show any nonlinear effects. You won't get harmonic generation or intermodulation from a linear model. Okay, good. So there are, that's a well-recognized fact. But what's not so well-recognized is that almost all the time, perturbation effects can be treated as a linear model. And we'll come later to a paper I wrote where people over the years have carped about the fact that, oh, well, it was only linear, it didn't work, Well, no, the perturbation part is linear, even if the large signal part is nonlinear in many cases. And there's a wonderful paper by a fellow I went to MIT with named Paul Penfield that I'll reference, and it's referenced in the paper that I put in there. So perturbation effects can be linear. That's a lifesaver. These are just some general ideas. So what's happened in the last 50 years? Well, I never worked in vacuum tubes. It was my hobby, but I just started in engineering as a profession at the time when there were transistors. Certainly there weren't integrated circuits. And the transistors weren't worth much, but that's what we used. And you burned them out wholesale. I mean, I still remember that feeling of, oh God, there go another 16 of them. We got to unsolder them and put in more of them. And somewhere along the line, integrated circuits came to the world. Moore's law has affected just about everything around us. I mean, I'll talk later about being on an IEEE committee that was very helpful to me, but we didn't have email, and we didn't have cell phones. I mean, we got on an airplane, 4-engine prop plane, and went someplace and all got together and used pencils and papers and argued by waving our arms. And it was a different time. So integrated circuits have led to widespread computing power, iPhones, all that sort of thing didn't exist 50 years ago. And the exponential growth of things like internet and Wi-Fi have changed the picture of everything. Now, if you can do something with in an integrated format with a heavy dose of software, that's the cheapest way to do it. There's no other way you can compare. That wasn't the case in the old days, and we barely got past firmware. People were controlling model trains with rudimentary software and computers and that sort of stuff in those days. What did I do? Well, I got my PhD in '62. By '68, I was ready to start my own company, California Microwave, which got out of hand, got bigger and bigger and bigger. I can assure you that the bigger an organization is, the dumber it is. And after 25 years, they said, enough, 2,000 children is too many for me. And so I retired, and about the next week, I got a phone call from one of the folks who was on my board, who was a professor here. He said, would you ever think about coming back to Stanford? Maybe we could do something. Sure. So that's where I ended up. So I've been here since '94. I always joked that because of having run that company and it worked out okay, I can afford to be a professor. And, but it's got some interesting lessons in it. And then one of the things that I never got in touch with when I was a grad student is the idea of standards. When something is produced, like your cell phone, okay, it has to work with a base station. There's a standard. Those standards are worked out by committees. I got on one of those committees very early on, and then I was on some other ones, and I discovered that's where the real education is. It's full of experts. Some of them are very political, or they're arguing about their company versus your company and so on, but I happened, luckily, in the first one to be on one that was very, very collegial, and it was very intellectual. And it had an objective that was a non-commercial objective, and I got the best education I could possibly have asked for. So that's what this talk is about. What can you learn from what's happened with me? I'm going to very quickly review oscillator phase noise. I'm going to assume that as you see this, you'll say, oh yeah, I know that, I know that, I know that. Okay, if you don't, break in and say, well, wait a minute, what's that supposed to mean? First of all, you know that the ideal output from an oscillator is just a single frequency, but the real world, it has some phase variation, also has some amplitude variation, but generally that's smaller. And I'll talk about the symposium I was at where the theoreticians all said, you must keep in mind the amplitude part. And the practitioners said, we're not allowed to spend any money on something that doesn't mean anything. That we've already looked at that 1,000,000 times and it's way so low that we don't care. And those two personalities are always at odds. But so the phase variation in an oscillator generally comes from some form of random noise. There are other sources. I'm going to ignore them. I'm just interested in the noise part right now. Turns out that the vibration and acoustic effects often are orders of magnitude stronger than the quiescent noise. But for now, let's pretend this is the most important problem. All oscillators are nonlinear, because otherwise they would draw all the power in the world and they would have a megawatt coming out or a gigawatt. And so they all limit somehow, either with AGC or with something that happens where it runs out of steam. Either it runs out of voltage, it runs out of current, runs out of thermal, whatever. So they all have some form of limiting, and that, among other things, is one of the reasons why the AM components are always less than the phase part. Also, at least in my experience, the application of oscillators was in a situation where we multiplied in frequency. Remember I said my master's thesis was on frequency multipliers in my PhD thesis. So that was, everybody asked me, okay, you know all about that, would you do this part? And I was active at the point where solid state microwave signal sources had a low frequency crystal oscillator and some frequency multipliers that we use for actors. And so that was what everybody looked at me and said, well, you went to school and you know all about that, so it's your job. Small noise perturbations, as I mentioned, generally can be treated with linear theory. And there's a paper by Paul Penfield in 1966, IEEE Proceedings in February, that was an eye-opener for me, partly because Paul and I were grad students together at MIT, so I knew when he was writing it, partly because I was an editor of that issue, so I got to read his paper before I had to write mine, and partly because it works out well. I was looking for it. Had confirmation bias. I wanted it to be that way. And so one of the questions that was of great interest to all of us, and I ended up drawing the short straw, was how do you derive the oscillator phase spectrum from the parameters of the oscillator? What are they? There's the oscillator power, in this case it was a high Q resonator, the Q of the resonator, the noise characteristics of the active element, fortunately, as you'll see, I was able to do that. Okay, so again, stop me if I go too fast, but I assume you've been through this a lot. One of the components of this way of thinking is that modulation and addition are the same thing. You can always take a modulative picture and convert it to an additive picture, and you can always take an additive picture and convert it to a modulative picture. So one interesting thing is, of course, the additive noise, when you're converting it to phase, depends on the ratio of noise to power or power to noise, depending on how you want to think about it. In cascaded stages, it behaves just like any other kind of additive noise. That is, it follows the Friese law of dilution by subsequent gain. That's not true in the case of modulative noise. If you have, for example, a typical thing is flicker noise, where flicker noise in a junction will modulate, not add to, but just genuine modulation on the signal, phase modulation typically, or amplitude, or both. If you have multiple stages, the powers all add up. So it doesn't get better like noise figure does when you have lousy downstream stages, but you dilute it out with the gain. Okay, now phase noise is important in a number of different kinds of systems. And as you'll see, this gave rise to a number of different schools that arose somewhat independently, and nobody needed to talk to each other because we had what we needed. And then something happened, which I'll describe, which caused us to have to talk together. And it was a wonderful result. First of all are the type of systems that you must be familiar with, that are phase. Phase is the essence of it. Okay, so phase noise means it's a limitation in some way. And it can either be phase noise or it can be jitter. And jitter is just integrated phase error over a frequency band. There are other systems in which phase noise results in a dynamic range limitation. A big signal with phase noise gets in the way of a little signal. So that's really a spectrum kind of thing, and not a phase thing, but it's related to phase because the spectrum of phase creates the RF spectrum. And then lastly, there's the whole area of precision, time, and measurement. This was the traditional area where people worked on how to make clocks that would be accurate to a part in a billion per year or a part in a billion per millennium or whatever. And so they were interested in time domain, but they became interested in frequency domain through a marvelous paper that was written by a guy who had not yet even got his master's degree, but it's one of the best papers in the literature. Wasn't me. Here's an example of noise on a QPSK constellation. You know, the fuzz can slop over and you can have a lot of errors. Here's an example of phase noise that masks an adjacent small signal nearby. Here's an example that I worked with. When you have a radar on an airplane, the beam of the antenna is never minuscule. And often it intercepts the ground. Well, the ground is 80 dB bigger than any airplane. And so here's this giant signal coming back from the ground, and you're trying to find an airplane by the fact of it moving. And so you get an offset, frequency offset, which turns out to be 10 kilohertz per Mach number at X-band, which is where the radars were that I worked on. And, but unfortunately, the noise on the oscillators that is imposed on the ground return, which is called clutter, gets in the way of seeing a small target. So it doesn't work. And so noise is a big deal in Doppler radars. And that's what I was involved with. Another issue that, I don't know why, but people make it some kind of a mystery. Reciprocal mixing is sort of a neat name. But basically, if you have a noisy local oscillator and a very clean signal, by the time you get through mixing them, the IF result is noisy. And so it isn't just stuff that comes out of the air. It can be introduced in a system as well. So these are all situations in which phase noise can be important. And as you'll see, they grew up in different dukedoms, different tribes. And it was very interesting how that happened. So I wanted to start a 50-year history with where we are today. Today, everybody knows all the answers, which is wonderful. First of all, in time domain, a fellow named Dave Allen, who's same age I am and still kicking, wrote a paper. He worked for the what was then the National Bureau of Standards. Now it's NIST. And their job was to provide time for the universe, or at least our part of it. And so they were interested in how do you measure the stability of a clock or an oscillator. And it turns out that some measures of stability are a nuisance to work with and don't converge. And he came up with a particular kind of variance, which is now called the Allen variance, that did converge, and wrote a paper about it. And it turns out that the Allen variance expresses itself in a power series. That is, any physical thing that we've come across, the variance is a power series with a very limited range of exponents. Which didn't have to happen that way, but that's just the way life turned out, which is good. Pardon?
One of the figures in the paper that you sent us, it shows that tau varies from -1 to 3. So how come here it's from -2 to 2?
I don't know. I think one is a thing called the modified variance, or I may have made a mistake in the paper.
For white phase is to the power of -2, to the power of -2. And for random white frequency is tau to the power of 1, tau to the power of 1.
I'll look at that and see. You may be right. I mean, I may have blown it. That paper was written in a little bit of a hurry, so you know, I get to be excused if I made a horrible mistake. But I'll come back to it because I've got a table that shows what I think the right answer is. A frequency domain, the Fourier transform of the variance is the spectrum. Goes back to early mathematicians, and so a wonderful thing happened. The spectrum also turns out to be a power series with a limited number of exponents. Now, we'll get the right ones before I get done. And here's a table that I think is correct, showing the exponents on your left for the power spectral density of phase, and on the right for time domain. Now, not every, and this is much easier to understand in a graphic format. So let me come to that. But the Allen variance has a typical graphical construction like this, where at each point in the amount of time you're talking about, tau, a different exponent dominates. And you don't always see them all. And in the frequency domain, the same thing happens, that there are all these possible different slopes. You don't always see them all, but they're possible. And the really interesting thing is that Dave Allen found a book recommended to him by his boss, Jim Barnes, both of whom Barnes got his PhD here in '65, so he and I didn't know each other. But he was Dave Allen's boss at the National Bureau of Standards. He said, Dave, look, there's a book by a guy named Lighthill, has a table on page 43, shows how a power series sigma converts to a power series S phi. And is that any help? And so Dave Allen had this problem he wanted to solve, and he looked on page 43, and there's the answer, and wrote this great paper called Statistics of Atomic Frequency Standards. So you can go back and forth between these two. And I guess I don't want to get into the details of whether I got the exponents right. The main point is that nowadays you can represent the whole problem in one picture. Okay, well, we couldn't do that. 50 years ago, it looked more like this. We didn't know. Oh, by the way, there are now 17,000 separate publications, books, papers, and so on in phase noise and frequency stability. So that, luckily for me, wasn't the case when I was active in it 50 years ago. So here's what it looked like to us. Okay, each of us had our idea. Well, this is our part of the whole picture. Okay, everybody was sure that I was sure the Doppler radar part. I knew all about it. And it's the white noise part. It's signal to noise ratio. It's very simple, and something happens at low frequencies. And the other guys had the opposite view. So the frequency and time guys, they were interested in frequencies, the inverse of hours and days and weeks. Okay, 10 to the minus 6, 10 to the minus 10th hertz. In those days, 1965 was when hertz began to use. So many of the old papers all talk about cycles and kilocycles and stuff like that. Everybody looks at it and says, what, didn't these people know anything? Well, it became a standard in 1965. And before that, we all used whatever the standard was then. Frequency and time folks are all interested in the low frequency range. And airborne Doppler radar, well, 10 kilohertz per Mach number, we're talking about closing rates of Mach 2 or Mach 4. The faster, the more interesting. So we're talking about 10, 20, 30, 40, 50 kilohertz. And all we could say, in a paper I wrote in 1964, one of my comments is, something happens at lower frequencies, it's sort of the noise gets higher. That's all I knew, okay? Separately from this, there was another application, which is frequency division multiplex in long distance telephony. And that's FM, and so FM noise made a big difference, and that's the same as phase noise. So they were expert in yet a different thing, and they used a different language to describe the levels of noise. And in the middle was kind of a no man's land.
Where does that offset come from, 10 kilohertz at 10 kilohertz? That offset of 10 kilohertz at 10 gigahertz? Oh,
just figure out Doppler effect. You know, Mach 1.
We have that offset.
Yeah, I forget it whether it's 10 kilohertz one way or maybe it's 20 kilohertz because of the two-way. But it's of the order of tens of kilohertz. And so noise at tens of kilohertz, of course, is very important because the ground is at one rate and a target which is moving, and of course one coming toward you is the one you want to know about most. It's at a different rate. You got to separate them, and phase noise made a big difference. Okay, so in the middle is sort of this no man's land. How did that no man's land get bridged? Well, an interesting thing happened. Around 1960, well, 1958, what happened in 1958? Sputnik was launched, and suddenly everybody got excited about rockets and space and this and that and the other. A lot of people had already been working on the question of space communications. And to get a signal from Mars to here, people were talking about 1 hertz bandwidth phase-lock loops. So now they're talking about something that's in that no man's land. But NASA had a lot of influence, and their influence, so they moved in, being explorers, they moved into no man's land, and they were very influential, and they determined that they needed to know about both of these guilds. And in fact, their objective was, if you guys would please put together a single standard that we could then appreciate. That'll help us and it'll help you. So science was moved ahead. And you can see they're talking about a 9 hertz bandwidth, and they're talking about a frequency offset of 100 hertz or something like that. So they're in the no man's land that none of us cared about. What happened was they convinced the Institute then of radio engineers, became IEEE shortly thereafter, that they ought to have a standards committee brought together that could bring all of the knowledge in a way that would unify the definitions. And they had enough energy and money to create a meeting and put the committee together. Luckily for me, I was able to be invited to be on this committee. I mean, here I am, this is 1963 or 4, and I got my PhD in 62, and I disappeared for 6 months because I was tired and came back, and I'm working, and a fellow named Bill Sanders, who was our customer at Hughes Aircraft, thought he saw in me somebody that would respond to some mentorship and some sponsorship. And he said, would you be interested? You know, you're the only guy who's fresh out of school, so you've got fresh neurons. By the way, when you get your PhD, that's the smartest you'll ever be. Don't let that bother you. You'll still be plenty smart, but that's when you're really tuned up. And so I was really tuned up, and he said, would you like to be on this committee? You bet. Luckily, I said yes. I mean, I just as easily could have said, no, I'm busy. You know, I'm working on radars, and thank you very much. But I luckily said yes. So I'm on this committee with all these famous people, Nobel laureates, people from the atomic standards, which were then coming online, people who knew all about the innards of quartz crystals and who knew about radar, and who knew about space requirements and who knew about telecommunications. It was incredible education. It was like you would imagine, I don't know, a Greek colloquium where Plato and Socrates are arguing about the right way to think about something. It was just incredible. So if that opportunity comes up, never say no to adventure. If you were so lucky as to have something like that happen, it's wonderful. As it happened, this was a subject that didn't have a lot of commercial influence. And I've been on committees since then where the commercial influences eventually kind of soured it, because everybody wants their own company to be the one that sets the standard. But that didn't happen here, luckily. It was very, very respectful. Everybody was good to each other, which I still treasure that memory. So our objective was to make a standard. And so here are some things we did. In 1964, we called ourselves a program committee, and we created a new symposium that hadn't existed called the Symposium on Short-Term Frequency Stability. And it was jointly sponsored by NASA and IEEE, and it was at a NASA facility. And then, as a result of that, we were asked to edit, as a committee, a special issue of the IEEE proceedings on the same subject, short-term frequency stability, which is wonderful. I mean, you know, it's great to be able to write something, but it's even better to read everybody else's stuff while it's still half-baked, and you can talk to them about, what did you really mean here? And they have to explain to you what you learned something. Again, now, no email, you know, some telephoning, maybe some meetings. It was not as easy as it is today. We got that done. By 1971, the committee was in a position to feel that we had learned enough that we could write a paper that would be the basis of a standard. And many years later, the standard actually appeared. So this process doesn't happen overnight, but the results of it can be put to use in real time. And so the fact that it took a long time to make a standard, by that time I was busy. I was making money building stuff that used the knowledge I had about frequency multipliers and phase noise. So, you know, at that point I wasn't even any longer a participant. New fresh PhDs had been minted and brought into it. So this symposium and the proceedings of it are online. I reference in that little paper I put out where to find the proceedings online. It's very interesting, especially the discussion panels, where you'll see discussions between people who are sneering at each other because you're just not a theoretician, so you don't know that this is important. And somebody else is saying, look, you know, we're spending taxpayer money and we don't want to fool around with stuff that makes no difference. And I can assure you we've measured it many times very carefully, and it's minuscule. And so these discussions were really kind of weird. And I'm in some of them, and I find myself thinking, oh, God, did I say that? Yeah. I was on the practical side. One of the things I looked for when I reviewed this for this paper was where did the first graphical evidence of these multiple sections, power law sections of phase noise or of variance first begin to show up? Because I find the graphical picture is so clear that who cares about the summation of exponents? You look at the picture and there it is. Well, there was one that had two segments in this paper by Jim Barnes and Dave Allen, then also in a paper that I had co-written with my office mate at Hughes Aircraft, we showed how the noise spectrum interfered with masked smaller signals. And so we were beginning, and that paper also had a calculation of the signal-to-noise ratio out far in an oscillator in the white noise region, showing that it was FKT over signal power, and that was, in fact, because of the conversion from additive to modulative, that was the modulation level of noise out there. And it says something about, and then closer to the carrier something more happens. So that's all we knew at that point. By the way, I'd strongly recommend, if you want to learn about something, read the papers, don't read a book. Whenever I've written a book, you don't, first of all, you don't have enough space, and secondly, you clean it all up. And you leave out you only see every fifth step. And so all the real stuff, oh my God, how are we going to make that work? Oh, look at it, it goes to infinity. What are we going to do about that? All of that disappears by the time it gets to be a book. But if you look at it in the papers, now you see hundreds of different instances of people saying, no, I think it's this way. No, I think it's green. No, I think it's kind of bluish. Something like that is much more valuable. So and you have the ability to download any paper. I mean, I've downloaded my own library of phase noise papers. I don't have all 17,000, but I sure got all the ones that have my name in it. It makes me feel good. So anyhow, then this special issue came up, and this is now 2 years later. And many of the papers are the same paper, given the hindsight of being able to see, oh, now I see what I should have said. Now that I've heard all the other papers, I see I could say it better, or I can clarify it. And so things began to clarify. Many of the papers are the same, many are new. But the same committee, with me tagging along, is going to edit this issue. And so we get all the submittals, including our own, and we read them all, we divide them all up. I get all the radar ones, somebody else gets all the timekeeping ones and so forth. Then we swap them. And the one paper by Allen really shines. We say, look, this really puts the whole time domain thing to rest. Look at this. It's great. And it shows how to convert from time domain to frequency domain if the frequency domain is also power law. All out of page 43 of Lighthill, the book about mathematics from England. And so then the question is, okay, well, so how do you derive the power spectrum of phase in such a way as it would work in that? And as we're reviewing these things, and everything's all put to bed, including my paper with my office mate revised on Doppler radar requirements and so on, and I'm beginning to think, hey, I think I see a way to combine the part of the world I know about and the part of the world that these guys have taught me about, and synthesize it. And so I ask about that, and the answer is, well, Dave, that's wonderful, but all the papers are put to bed. It's December, and we're going to be publishing in February, okay? And so this Allen variance paper is wonderful, and I'm wanting to know, how do I get SV of F from FQ P sub S and the frequency? So I want to meld prior and new knowledge. I want to synthesize. That's how you get new knowledge. And but I'm only given 2 pages because they say, look, it has to go in the correspondence section. Too bad. And 2 pages is the limit. We've kept some pages open in the correspondence section. There's no room for another paper. So whatever you can do in a month and in 2 pages, do it. Well, okay. Luckily, these guys were incredible mentors. I mean, every time I had a question about, well, how does this work? Boom, I got an answer. It's either a paper we already read or somebody who wrote it already knows it. So it wasn't too hard by that time. And I made sure I was educated enough to be able to understand what they were saying, which is your part of it when you get a sponsor or a mentor. And that's a picture of me whacking the thing out in a month. Okay, so that's the result was this 2-page paper, the phase noise model. That and if you get something named after you while you're still alive, it's really an amazing piece of luck. And it didn't happen on purpose. I mean, I've seen people name stuff after themselves, you know. But no, I can promise you, I ignored this for 25 years. It had a life of its own, but somehow it was good enough, thanks to all these mentors, that it persisted. I wanted to find the power spectral density of phase as a function of Fourier frequency for a single resonator oscillator. That's the kind I worked with. I mean, nobody in those days had even thought about using delay lines, or, you know, it hadn't been thought of yet. First of all, I knew that inside the feedback bandwidth, that was already well known how a phase error converts to a frequency error, and everybody knew that. Nobody knew quite what to do with it. There were wonderful papers about that, but they didn't have any application to anything. In my own paper, and I'm sure it didn't originate with me, but I knew that outside the feedback bandwidth, feedback doesn't have any effect at all. And so I could immediately figure out what is the power spectral density of phase at the output. It's the same as at the input, and it's FKT over P sub S. We were using 2-sided spectra at that point, and went to 1-sided spectra, and so there was a factor of 2 that bounced around that people always used to tease me about. But you know, you can see the 2 was, I mean, that's mighty close, and you can figure it out. Okay, so and I put together a graphic picture of how you went from what I considered to be the, this doesn't work, does it? That screen is so absorptive that you can't shine a light on it. On the right is a picture that's from the paper that shows the power spectral density of the phase error in the oscillator, which includes the flat part, the white part, and it includes a 1 over F, a flicker part. This is now power spectral density. And almost all flicker effects have a power spectral density of 1 over F, which bugs everybody because, of course, they say, well, wait a minute, that means there's infinite power at 0. No, there isn't infinite power at 0. You don't have that much time. And there are a lot of other ways to handle it mathematically. But as far as you can measure, it's still 1 over F. So, so those 2 pieces could be put together in a single transfer function. God, it looks simple now. But I mean, it wasn't then. Nobody else did it. And you know, I wasn't sure this was right. And I made the mistake of calling this heuristic. A heuristic is a word that means it's more experimental than deep theory. But it wasn't. I mean, I knew this was the right kind of transfer function for a feedback network, for a servo like this. That's all the way it always works out. So, you know, when you see something and you say, oh yeah, I saw that in servo class, or, you know, I saw that and I said, okay, that's the right answer. So on the right at the bottom is theory, and here's the measurement. Very satisfying. You know, showed the 3 segments. The one closest to the origin is the flicker of frequency, then white of frequency, and then there's a crossover point, which is about the, you know, what I could tell from any way I could measure it, the bandwidth of the feedback network, and then white noise from there on out. First time anybody'd seen this, you know, which is just amazing. I mean, it's sort of like, you know, you're walking down the street and you look down and there's a half a dollar or you know, something on the sidewalk, and you pick it up. Everybody else has been walking by and nobody ever looked down to pick it up. Well, of course, you have to be trained and sensitive to what it is you're looking for, and being on this committee was incredible training, much better than you'll ever get in any kind of a graduate school. So that's why I say, when this opportunity comes up, now that you're qualified, take it.
Excuse me, Professor, I had a specific question about the 1966 paper that you overestimate F as 9 dB.
Oh, I'll tell you about that. Why is F 9 dB? That's, people have been poking at that. Everybody says, oh, well, Dave didn't know that's just a fitting factor. He must have fiddled it. No, we didn't. We had transistors in those days had a 5 or 6 dB noise figure. And I'm a nonlinear guy, huh? So let me explain this. I know that this is a nonlinear device, but I also know that it isn't a terrific mixer. And I estimated that, well, maybe it's another 4 dB that's noise mixed in from the harmonics. Now, the noise brought up from the baseband, the flicker noise, that is a linear modulation. That has nothing to do with nonlinearity. It'll happen whether it's linear or nonlinear. It's something that's time varying. Okay, so that doesn't apply to the flicker part. But the white noise part, I was perfectly happy with. I was one of the authors of one of the first papers that showed how intermodulation has an intercept point. I mean, that was my bread and butter was nonlinear stuff. So it isn't a fitting factor. It was the best transistor you could get had a 5 dB noise figure, and I figured it added another 4 dB. And interestingly enough, this is now awful lot of years later. One of my lessons from an attorney that worked for us once is if you have the paper, you win. And he taught us to have paper and wave it. Well, okay, here's a paper that is called Study the Correlation Between High Frequency Noise and Phase Noise in Low Noise Silicon-Based Transistors, 2004, 3 French gentlemen. And what it does is it says, we can calculate the large signal and measure the large signal noise figure, and sure enough, it comes out to fit Dave's model. So I feel very good about that. I mean, there's also a paper somewhere that says, look, you didn't know anything. What an idiot. I don't like that kind of paper because I never write that kind of paper. If I find something wrong with somebody else's paper, I always say, look, this is a very uncharacteristic mistake for a person of that genius. But it's just an extension. It isn't that they were wrong, it's just that this is a new thing that they didn't even consider. And I'll show you one thing I didn't consider. So anyhow, I knew about nonlinear stuff, and 9 dB seemed like a good number. I mean, it's approximate, but it wasn't less than the noise figure, the small signal noise figure of the transistor. I mean, these were really early days transistors. Okay. I was able to, in this paper, to suggest that with a graphical construction, you could see where you would want to choose the crystal oscillator frequency if you're going to multiply it a lot. And the answer was as high as you can get, because unfortunately there was no room for the graphic. This is the missing graphic that's alluded to. I mean, all I could say was, you could easily see with pen and pencil, ruler and some paper and pencil, you figure this out yourself. That's all the space I had for left. But you can see that if you make the assumptions that Q is inversely proportional to frequency, and that the signal noise ratio is constant, which is a lousy assumption, but it's as good as any other assumption, that you right away see that, you get a lower noise far out if you multiply only up from 100 than if you multiply up from 5. So, good. And it mentions that in there. And that's what we always used. One of the things I also mentioned is that the flicker noise can obscure this crossover frequency in some cases. That's not flicker noise of the resonator, it's flicker noise of the transistor, of the active element. I missed the flicker noise of the resonator because flicker noise doesn't show up in VHF crystals. It only shows up in much higher Q crystals, 5 megahertz crystals, and that was discovered by somebody else, and people have added that onto the model, and that's the right way to do it. The best discussion of this is by Enrico Rubiola. If you want to know about phase noise of oscillators of the type that I'm familiar with, then Rubiola's book and his papers are really terrific. He's really dug in. As I mentioned, there's not flicker noise of resonator considered by me in the paper because I didn't know about it. And other people knew about it because they were working with 5 megahertz oscillators because they needed the kind of stability that long-term stability that oscillator had. In a radar, the only amount of stability you need long-term, how long is long-term? Well, out and back at the speed of light, at which point long-term is over. It can't go very far. That's long-term for a radar is when it's had one round trip. So we weren't concerned about everything being stable over a year or a month or something like that. Not like a channelized system. Okay, so by 71 we published this paper, and you've all heard the story about that a camel is an animal designed by a committee, and this was a camel. I mean, we really, each of us had our own part of the elephant still, and we all wanted to have our part be the most important part, and it was The chief editor was Jim Barnes, who was a wonderful guy, but he was a frequency domain guy, time domain guy, so it dominates the paper. But we all got our licks in, and we all went away happy saying, okay, now somebody can use this to write a standard. But if you ever, in those days, it wasn't common to have a large group do a project or write a paper. So that was really quite a project for us. Since then, there have been a lot of papers written. I mentioned there's 17,000 references. One of the things that tickles me is I was looking at Google Scholar, there's something like close to 3,000 citations of my own paper. It's the most cited paper, which happened entirely by accident as far as I'm concerned, because I was busy with something completely different while it was out, running its own life. I mentioned the nonlinearity issue, and I'm satisfied that in the high Q oscillator case, that a linear treatment is adequate, even for a nonlinear, and the Penfield papers is the reference for that. And I mentioned this paper that had the prediction measurement of large signal noise figure and showing how it's a few dB more than the small signal noise figure because of mixing of noise from the harmonics. However, integrated circuits created a totally different environment where the kind of oscillator you would want to know about, I mean, the purpose of all this theory is so you can tell how you're doing and what do you do to do better. And is it enough? Once you get to enough, you stop pushing quite so hard. At that point, it becomes what some people call, as a professor, I don't like the phrase, but academic. But it's not commercial or industrial, but academic problems are also wonderful. At any rate, the strongly nonlinear situation, I happen to have a hand in that by accident. I was teaching EE 344. I gave a lecture on my model of phase noise, and a young graduate student named Ali Hajimiri came up afterwards and said, do you think there's any life left in studying this in a different way? And I said, sure. And he said, because this doesn't really apply to low Q oscillators like, that we use all the time in integrated circuits. And I said, well, great, I encourage that. How can I help? And he said, well, Professor Lee and I are going to work on it. And so, I did the most I could to encourage him and, offer suggestions. And I was very happy with the result, which is the Lee and Hajimiri work on strongly nonlinear oscillators, which tells you what to do. Tells you how to design it, how to make it, what to avoid. Balance is important, this and that and the other. Very useful. And then further work's been done at Bell Labs by a group under Alper Demir. And it's just at the boundary between being difficult to use but absolutely correct. And so, that's one of the problem areas that one of the things that's kept my paper alive is it's simple. I mean, anybody, can look at it and say, oh, well, if that's the right answer, I can understand that. Much more has been done in areas, but it's harder to apply. But nowadays, with the ability to use software to design things, we didn't have software, we didn't have computers. We didn't have calculators. And we had calculators that had a crank on them, like in a bank, which is something I used when I worked in a bank when I was a kid. So that's made it possible to use more complex ideas and not get your brain all scrambled up that you can't keep track of it. And so that's a wonderful paper also. Different kinds of resonators have been used, and it's been pointed out that, well, you don't have to use Q, you can use tau, the delay time. And then you can take into account many different kinds of, and there's a tau for a single resonator, and there's a tau for multiple resonators, there's a tau for delay line. And that's a good extension. A paper by Mike Driscoll is one of the first I found on it. This flicker of resonator has been handled by adding a term. It was noted in a paper in the 66, I'm losing where I am, the 66 issue of the proceedings, but I didn't notice it because it was in an area that wasn't of interest to me as a radar guy. And that's been handled. People made wonderful measurements showing that resonators themselves had flicker and that you had it included in the model. It seems like almost every physical thing has flicker. Flicker noise, flicker variations of some sort. There was a big argument about, well, look, if it's 1 over f or 1 over f cubed, then it's going to have infinite power as it comes near the the carrier. No, it doesn't have infinite power. That's the modulating signal, not the RF signal. And so the question is, what's the relationship between the power spectral density of the phase, which is this 1 over f cubed, and the RF spectrum, which is not infinite power. It's, one of the things that an early paper said, imagine noise being modulating an FM oscillator. So same power, no matter how hard you modulate it. What's the spectrum look like? We need to know that because that's similar to the spectrum of a frequency division multiplex telecommunications system. It was a sort of a shorthand for multi-channel multiplex by just putting in noise instead. And you can see right away, oh look, it's not going to have infinite power. It's just going to get wider, and maybe it'll eventually have so much deviation that it'll obey the Carson law. But you know, that's a problem that's been solved anyhow. It was solved early in a horseback way, and more recently in a very elegant way. You know, the answer is don't worry about it. for the kinds of systems I'm involved with. Yes, you have to worry about it. It has to do with line width. It's actually a way of predicting line width in a laser or an atomic clock. What about AM to PM? Well, eventually it's been revisited, and amazingly enough, instead of saying it doesn't matter, now some people, my pal Hadi, I forget her first name, but at NIST in Boulder, I went to visit there when I went to give this talk, and they measure the AM noise, and they say, well, look, the AM noise has got to be somehow correlated with the PM noise. How about if we use the AM noise to balance out and remove some PM noise? So instead of it being a bad thing, we'll make it a good thing. And they did. And they were able to push the noise down by 10 or 15 dB. You can never cancel anything by a whole lot of dB. Some people will say, well, you can cancel it by 80 dB or, you know, no. That's balancing something on, you know, on the head of a pin. Nothing stays that good in real life. But 20 dB sometimes in a digital system is the difference between hooray and I can't hear you. So Archita is her name. And then lastly, I promised this isn't about vibration, but vibration is something that people have noticed is now hasn't got better at the same rate as quiescent performance. And more than that, people are looking at ways to cancel out vibration sensitivity of different kinds of resonators by measuring the phase shift in an optical fiber when it's vibrated and things like that. So a lot of really interesting things are happening. Plenty of excellent papers. Okay, so what's happened then? As a result of this 50-year project, there's a standard. There are a whole bunch of great books, including the Lee and Hajimiri work. And the best book, and there's a wonderful report by a fellow who is hired by NIST, National Institute of Standards and Technology, to write a report. It's wonderful. It's got all kinds of, you know, red and blue and green pictures in it and so on. And it basically is a picture of everything. Everything you ever want to know about frequency stability, time stability, whatever, all in one place, which to me says, okay, it's a solved problem pretty much. There's still lots to do, but I mean, it's not a frontier. And my colleague Enrico Rubiola has written what I like best, because he is a really capable combination of an experimentalist and a theoretician, and very, very energetic guy in this area. So now we can see the whole elephant. You know, before we had people poking around at different parts of the elephant. Now the whole elephant is visible to anybody who cares to do a little look in the literature, which is, you know, I mean, 50 years is not that long. So what are the lessons? What did I learn? Well, finding a mentor and a sponsor is absolutely key. And I've been very fortunate to find people that, you know, would tell me, look, I'm interested in this. If you're interested in this, I'm willing to help you. If you're not interested in this, tell me now. You know, there's somebody else here who's interested in that. I'll send you over to them. And that is that's why you're here. That's why you're not taking online courses. Not because you can't absorb the material, but because you can't get a mentor or a sponsor by remote control, and not by email. And you have to interact. And when you find one, then you have to decide that is going to be your specialty, and you are willing to dig in and read all those 17,000 papers, including the ones that are totally inscrutable or the ones that are wrong, and go to the symposia. And when somebody says, "I'm editing this thing," "Oh, can I help?" You really have to move toward it. Otherwise, you miss it. And it may not be your objective in life to do that, but I think most people who come this far want to do something special. They want to realize their potential. You could do it, you just want the chance. Okay, well, this is the method, one of the methods by which you get that chance. How do you go about this? Well, this is the hardest thing. I read an interesting thing that pointed out that nowadays there are infinite answers, and so the real value is in finding interesting questions. You can find the answers to any question you can pose somewhere. I mean, not always good ones, but questions are hard to come by. And questions are what you get from your mentor or from people around the mentoring process. And you want a question that hasn't got all the way over the peak of publication. In a situation where there's 17,000 papers and books, you're not going to find anything big and new picking through that pile. It's not like walking down the street in an area where nobody ever lived before, and you look down and you pick up an arrowhead or something like that. Okay, all the arrowheads have been picked up in some fields. In other fields, they're brand new. So and the talk that we heard on Tuesday had some interesting ideas. I'll just give you a hint of how I think about this as a former business strategist. In satellite earth stations, we used to make giant ones, like the big dish. And there were a few of them. And they were very specialized, and a company like us that knew how to hire a bridge company to do the welding, and we did very well. And then they got smaller, and they were put around in newspapers, and we made 100 of them and 120 of them in Alaska, and every newspaper had one and so forth. And then they got to be backyard deals, and now they're a little thing that goes on the side of the wall, and it's a consumer product, and there's millions of them. And the people who knew how to make those great big dishes are infrastructure people, just like the people who know how to make cell sites. And the people who are going to make the future cell sites are consumer product people. And so it's a whole new deal. Just an example of how to think about something. When somebody gives you a lecture about their picture of the future, try to extract from it, how does that relate to some things I've seen before? That's what history is about. You study history so you can say, oh, I've been here before. The next thing that happens is, just like in backyard dishes, go down to little tiny dishes, and everybody gets television, off a big satellite. And sure, there has to be some central infrastructure, but then it makes possible having millions of these things. Same with cell phones. Cell phones are not infrastructure; they're a consumer product. But right now, cell sites are infrastructure, and they will become, at least in part, a consumer product, just as the outlets on the wall. And, in the old days, you didn't have power every six feet, every 2 meters. Nobody figured out that that's as far as the cord on a vacuum cleaner should be allowed to go. But now every building that gets built has to meet that. And so you go down to a hardware store, and for 39 cents you can buy an outlet. Well, something like that's going to happen in cell sites, just as an example of one thing. It's going to look like a cell phone. It's going to use the same circuits that are in a cell phone, integrated circuits. It's going to have to be something that, like a Wi-Fi hotspot. Wi-Fi hotspots, I was on the Wi-Fi committee also, I'll come back to that. But basically we gave up trying to make a perfect theory, but we forgot that it was only going to cost 50 cents to buy the IC someday. And so you could just have as many of them as you wanted. We wanted to have a few hotspots that would handle 100+% offered load, and we couldn't figure out how to do that. Then it collapsed into arguments between different companies, and I got disgusted and left. But eventually it turns out, well, you just get down to fries, and for 20, 30, 40 bucks, you buy a hotspot. So that's a trend in things, and if you're in the RF integrated circuits, that's going to be something you're going to contribute to. I mentioned reading the original papers. Seeing people sweat over their lack of understanding, is really the way to educate yourself, in addition to that personal connection. And by the time it comes to a book, I wouldn't write a book where I gave any hint that I didn't understand the whole thing. And any hint that it was, anybody ought to be able to go from here to there, don't bother me with the details, the correct exponents, I don't care about that. It's an exponent. You know, the original papers have all the details. Somebody gets to reviewing it, they don't do so well. One of the things I recommend to people is that you be good at two things, or at least you know about two things. One example is an engineer who is an attorney can be a patent attorney, but not every attorney can be a patent attorney, and not every engineer can be a patent attorney. So these themes have way less competition. They're specialization of a very important part. That's a strategic idea called segmentation, and you want to be differentiated in your segment. A segment is a part of a market that has some kind of a defensible boundary around it. In my mind, I think of one of these 18th century, wood arcade forts, and inside you're safe, and outside, no, going to get picked off by the big guys. So, and these are two examples. RF, being good at RF and being good at semiconductors, that's a combination not everybody has. Being good at wireless and being good at networks is a combination not everybody has. So these are just examples of how to combine things. And that's what happened to me. I was good on the radar side because I'd been educated there, not because I made it up myself. And after a while, because I was exposed to the Standards Committee and these people, I began to understand what they were talking about. And I said, hey, they don't happen to understand what I'm interested in, but I guess I could adopt their kids and raise them. And so I'll know how to know both. And then I figured out how to put them together. And then, if you're the first one to find something, you get the prize. If you're not, you get to write a paper about how the person who did wasn't so smart. If that's your direction. Okay, and then lastly, the standards process. That's something you don't get any education in. I didn't know about standards process. I just happened by accident to get invited onto this committee. What happens in the standards process is, in the case of a technical standard, there's wonderful argument going back and forth. Think of the building codes. Somebody will say, look, the building has to be so much iron in it, and the answer is, well, we can't afford that, so how can we compromise? So what is one of my specialties happens to be, I live in a very windy area. We get 150 mile an hour gusts, and my antennas always used to blow apart. And my wife convinced me that since I was an engineer, I should stop patching them back together and write a book about it, which I did. And now I know more than I need to know about that subject. But I mean, and standards have evolved by people pointing out, look, let's get together and talk about how come buildings fall down in the wind, or they vibrate, or they fall down in earthquakes, or well, the same thing happens in electronics, in communications, in semiconductors. Some standardization happens because there's only one great way to do it. And CMOS is a good example of it. If you can do something in CMOS, great. Okay, now you're golden because it's all understood and everybody knows what to do, and you just, you go over to the fab and you get some. But some standards have to be thought out, and this frequency characterization was one that had to be thought out by people who didn't really care a lot about other people's needs, but cared enough so that we educated each other. And so I recommend that. Look for things like that happening. It's a wonderful experience. The way you get on those things is you publish. And so one of the characteristics of a good mentor is somebody who can help you publish. I had a mentor at MIT who helped me publish. In fact, I published my master's thesis first and then turned it in as a thesis because they had a policy that you had to get their permission to publish. So I published it first. And I said, okay, now this is in the proceedings of the IRE. Would you accept it as a thesis? It's a famous paper already, and so how about it? And they said, sure, okay. At which point I hopped in my car and left because I wanted to get back to California. And I had the opposite thing happen here, whereas my thesis advisor disappeared. I came back from a summer working, and I went to make an appointment, and I was told he's no longer with us. Oh my God, he died. And it turned out years later, and so I had to find somebody else. Well, I had to find somebody that was, that guy, my original guy was in my field, and it was, perfect for me. But the new guy, he just was somebody who didn't have any students. He later ended up being famous here. But I wasn't in his field, he wasn't in mine. I got done, he didn't help me publish. And I just, figured, okay, I got out of here. I also left just before the first semiconductor lab was launched here at Stanford, and I wanted to take it because I wanted to learn how to do that, and they said, no, you're done, we got to make room for somebody else. So I never got to be a semiconductor guy like you guys. Years later, I got interested in history, and I'm doing the biography of W.W. Hansen. Hansen is a guy who is more than any other individual, except maybe Fred Terman, responsible for Stanford being the internationally famous research institution it is. He was the inventor of the linear accelerator, nuclear magnetic resonance, Doppler radar, pulse Doppler radar. He wrote the book on radar during World War II at the MIT Radiation Laboratory, and at the same time he was working the other 5 days a week at a different place where he had to go back and forth by boat. And before the war, he and his roommate Russell Varian invented the klystron. That's how it happens. You know, Varian was a dyslexic who was very inventive. Hansen was a genius who could read very well, and so the two of them made a great team. And Hansen helped his roommate finish his master's thesis and get it published, and the two of them were partners for the rest of their lives. And they shared an office, and they taught. Hansen also invented the microwave resonator as a result of discussions with Varian. And Varian, because he was interested in invention, had worked for the inventor of television and had learned the local best patent attorney who he brought to Stanford, and that's where all of the Stanford patents, including the Hewlett and Packard patents, came from. So it's a very tight-knit group. Anyhow, so publish, important, join is important, don't miss out. You know, I was really lucky. I didn't know what I was getting into. I just had this instinct that, you know, this guy said, you should really do this. You know, take my word for it. And, you know, I owe it to him. Then I was able to start a company in 1968. Here at 66, I published this paper, and I've worked on frequency multipliers already. By 68, I knew all the customers because they were the guys on the committee, and I started a company to make signal sources for radars, to commercialize the technology that I knew about. And at that point, of course, my publication stopped. We went public a couple of years later. When you have shareholders, they're not amused by you giving away all the secrets by putting your name in the IEEE proceedings. So there was sort of a quiet period where I didn't get to say much. And 25 years later, I retired and came back here, and I looked around, and oh, my paper's still in circulation. People still like it. It still does something useful. I thought I was the only one who was using it. And we did very well. You know, it became a big outfit, and all I wanted was a back room with a spectrum analyzer all my own, and it kind of got out of hand. But, and I think if you think about entrepreneurism, to me, we had one objective, to be a decent, honest success. We wanted to be as good as we could be. We didn't care about the money. As it turned out, you know, we did well. But to me, you know, the idea of going into business to become a billionaire is, and I've since looked at investments in situations, and every time I've said no to somebody who said, oh, I know how to raise money. I've got this terrific idea. You know, I know how to raise money. Okay, good. Go somewhere else. You know? And I'm attracted by people who say, no, I have this idea. I just want to do it, you know, and I can't find where I fit in, but I'm going to do it. So that's the story. Questions? Hope this is helpful. You didn't learn anything about phase noise, did you? But and I'm probably wrong about the exponents. I apologize for that. I'll look into that because I've found several other errors. I didn't misspell my own name, but I misspelled Dave Allen's name on this. Is a lifelong colleague, and I always forget to make it A-L-L-A-N. But so, any questions? I'm sorry?
Is there any room for future work in this area?
In phase noise?
Yes.
Well, I'll tell you where I would look. My wife and my wife's a psychologist. She works with disabled students in the OAE here. She actually works with dyslexics, so she knows all about Russ Varian and Bill Hewlett, who are both dyslexic. And she's funded by Charles Schwab, who's also dyslexic. So they're not bad not to, you know, the people compensate. If you have one thing that you're not so good at, maybe your mind improves something else. Anyhow, we went to Denver to give this talk, and I said, I'm going to go up to Boulder and meet these people at National Bureau of Standards, at NIST. What a neat group. Everybody is supportive of each other. Nobody said a bad word about each other. They all wanted to, come on, I want to show you so-and-so's work, you know, and this and that and the other. My wife got real excited because everyone had their picture taken with me, which I thought was kind of amusing. But, you know, that's the part of the world where phase noise is, that's all they think about. So that would be where I would go to inquire. their most recent technical member is somebody who came there as an intern and then stayed and was brought in. Government funding is always tough. So, but they seem to be doing very well. They showed me a little integrated circuit ring resonator that can be done laid onto silicon that has incredible Q, more than you get in MEMS resonators, which is another thing that there's a lot of work on. MEMS resonators was something that nobody gave much hope for, and all of a sudden, whoosh, they went right past crystals, and now SciTime is doing $1 million a month or something like that, a million ICs with resonators in them. So I wouldn't say no, but I'm not coupled into that. But I would talk to people who are in the business. Every year there's a frequency control conference, International Frequency Control Conference. I've got the proceedings from the 1991, and I went to one, back in the days when it was in Atlantic City in a hotel for old people. Now I am one. But that's where to find out what's happening in phase noise. When I was at this symposium, I hadn't been to one in years. And when I got there, I'm looking at the slides and I'm listening to what people saying, and I said to Barb, God, these are my people. I know what they're talking about. This is actually something I know something about. And it was very interesting. In a place like Stanford, everybody is more famous than you. And so, so you did this or you did that or you did the other. It doesn't matter. Everybody on the faculty is doing important work. But there, it was kind of fun to be in a situation where somebody, oh, I know your name. I read a paper by your uncle. No, it was me. No, it must have been your uncle. So that's where I'd look. Look at the. You can go to IEEE Explorer and search IFCS, International Frequency Control Symposium, and see what the current papers are. And among them, you'll see some that are questions, or there are some that are like summary papers. There's a wonderful guy named Ulrich Rohde, who writes constantly, more than you could have ever imagined. And his specialty is sort of summing up things, so that you can sort of see, okay, how is it all worked out? And there are other people who write about, okay, we got this problem, we don't know what to do. A lot of the work now seems to be going on in France. There are two people in France, Rubiola, and another guy named Routman, R-U-T-M-A-N, Jacques Routman. And they have labs which have developed out of the Swiss watch industry, essentially. They come across the border into France, and they have institutes of time and precision frequency and things like that. And they're doing a lot of work. So those are people that you could email and say, I heard a talk by this guy, Leeson, and he couldn't suggest anything, but he said, maybe you can tell me. And that's a place to start. I have to say, though, that in a field where as it gets more and more mature, it gets more and more specialized, and you have to dig deeper and deeper to find a truffle. When I was a kid, you just found them lying on the surface. And now you got to really snuffle in there and find out what's the part that hasn't been handled yet. But there's still a lot to do. There's still a lot of unknown questions. Phase noise is very important, for example, in synthetic aperture radars and in these big radio astronomy arrays, because you want to have time correlated over huge distances so that you can then make an interferometer that has a 10 to the minus 10th angle. So there's still a lot of work to be done on how to do that. And atomic things have come along, the MEMS things have come along, different types of resonators. There's a lot of work on that. A lot of the resonators people had a lot of hope for haven't worked out. They just turned out to be useful enough, but they didn't take over the world. And quartz is still a big deal. Very interesting book on a reference in there, and the third reference, the story of quartz resonators in World War II, and how it started from something that hams did in their kitchen with a bonami and ground them around to something where they had to make $2 million a month. And then they all quit after about 2 years, and a guy was put in charge of finding out why and fixing it. And how'd you like that job? But anyhow, that's sort of the, I'm more interested now in history than I am in the future because I have more back than forward. But I'm still interested in where this is headed. So, any other questions? Okay. Well, I hope your career is as satisfying as mine's been. It's just been very lucky. I mean, to be a ham, 63 years, and I'm still working in my. I get paid to do what I would do for free because it's fun. There's a course given by John Pauly where people end up getting ham radio licenses. And John Pauly is a guy who's worth knowing. He's known to be one of the best sponsors in the business, one of the best mentors. When you read the thesis acknowledgments, you can always tell whether it's, yeah, well, thanks to my advisor, or this was a real person that took me into his home. His wife cooked for me. He fixed it up with my girlfriend. He was always there to answer every question. Well, that's the kind of mentor you want, okay? So, and Amin is like that. I think Amin is developing into a really first-class mentor. And I'm tickled to see his development because I started, being a little bit of a mentor to him when he had just first arrived and, was kind of wandering around. And he said, "Yeah, I keep getting in trouble with this or that or the other. How do I do it?" And I ignore it. Just do something famous, and then that won't matter anymore. But other questions? I'm sorry I can't answer that more. If I had a problem, I would give it to you. I promise. But at this point in my career, I am in 2,500 pages into the Hansen biography, and I'm not done yet. And I'm going to be done by 2009 because that's the 100th anniversary of his birth, and I've just missed it by a little. But I'm going to get there. And his archives are here. The Stanford Archives is wonderful. They have all of his letters to his mother. A little handwritten letter, "Dear Ma, I guess I didn't write you because I got in trouble here. I flunked my German exam and I was feeling kind of bad." And she writes a letter to the professor saying, "What's the matter? You're not helping my boy, and maybe I was a bad mother." And she quotes a newspaper article that says that Stanford wants exceptional people, and she has an arrow pointing to it. "Is this still true?" And he writes a letter saying, "Mrs. Hansen, don't worry, and we'll take care of it. He's going to learn German enough to get through here." And all the way back to that. And a thing from his childhood where he solved an arithmetic problem, and his parents thought that was so great they got an aunt to write it up on it's not his writing, so I can tell it wasn't him. But, but I mean, it's wonderful to look in the archives and see the real stuff. So he died, by the way, at the age of 39 from beryllium poisoning from his thesis, PhD thesis. So you don't always get a lot of time, but what he did in 20 years is more than a lifetime for many other people. So he was what Fred Terman sold to the government after the war. Terman was in charge of a secret lab for radar countermeasures at Harvard called the Radio Research Lab. Labs were always called something that didn't mean what it was. The radiation lab was supposed to make you think it was about atomic physics, and then they realized, oh God, we do have atomic physics work going on. We shouldn't have named it that, but it was named by Lawrence of Cal. He was the guy who was brought in to hire the physicists to do that, and Hansen was brought there to train him. At the end of the war, this lab that Terman was put in charge of had 800 scientists, bigger than Stanford, bigger budget, more things happening, and he asked his secret customer, when you're in the secret business, you can't talk to anybody except the customer and the guy that they've hired can talk about secret stuff. So they don't talk to anybody else because they're afraid they'll blurt out, "Oh, by the way, we're going to blow up the moon." "Oh, did I say that?" So he asked his sponsor, "What are you going to do with the money after the war? Are you going to just stop, or do you think that science is going to continue?" "Oh, no, we're going to fund things." "Well, what would you like me to do?" "I want you to hire your top 12 guys from your Harvard lab, and I want Hansen. And I'll put millions of dollars every year into Stanford as a result of that." So Hansen founded the microwave lab, and Terman founded what was then called the Stanford Electronics Labs. I worked in the basement. My office was in the basement. I had a 200-watt light bulb that kept me and my desk mate warm and lit in a coffee can. We painted it black and it smoked, but it worked. Anyhow, that was how Stanford got where it was. And then, of course, eventually it got in too deep. And during the 1960s, late 60s, people objected to Stanford doing that kind of work. But by that time, it was already launched in donors from companies that had started from Stanford. which is why I was willing to come back to Stanford anyhow. I think it's a neat place. So, anyhow, that's what I know. Now you know everything I know. There's no more. Okay.